Hello, Psych 299 statistics students. This is Larry Hatcher. We're now at part 140, 2A Anova with two between subject factors. I hope you have your course pack in front of you. The course pack section headed part 140, 2A Anova, two between subject factors, beginning on page 140-1. A lot of the important terms in your course pack are blanked out, and we will fill in those terms as we go through my lecture. Here's the outline of what I plan to cover. 2A Anova. We'll talk about what is factorial design. We're going to see this expansion of the ideas that you learned about when we talked about one-way Anova. We'll talk about factor A and factor B, give you a fictitious illustrative investigation, go over some of the terminology in two-way Anova, what is a cell, and importantly, most of this lecture I'll be talking about the two kinds of effects that are possible when you do two-way Anova. What is a main effect and what is an interaction effect. This will result in an online quiz in which you'll look at figures that illustrate possible results from two-way Anova, and you'll estimate which effects are probably statistically significant given the pattern that you see in those results. Introduction, basic concepts, two-way analysis of variance, two-way Anova. In previous chapters, we talked about single factor experiment in which you manipulated just one independent variable. But as long as you're taking the time and effort to conduct an investigation, why not manipulate more than one independent variable? Yes, this is possible. It's possible to use a factorial design. That's a research design in which more than one independent variable is manipulated. In two-way Anova, we'll refer to the first factor as being factor A. We'll refer to the second factor as being factor B, and all throughout this lecture I'll be talking about factor A and factor B. Some of the terminology, some of the jargon we use with two-way Anova. In a two-way Anova, it's a lot like conducting two one-way Anovas, but it has important advantages. A little bit later, we'll see that there are types of effects that you can investigate with a two-way Anova that are not even possible with one-way Anova. More of the jargon. If you've conducted an investigation in which you have two independent variables, you'll analyze it with two-way Anova. That's what researchers mean when they say we analyze the data with two-way Anova. If you had an ambitious investigation with three independent variables, you'd analyze it with three-way Anova. A four-way Anova is about as sophisticated as things get, and in this class we're not going to be any more sophisticated than talking about two-way Anova. Example of a study. This will be our fictitious illustrative investigation. Let's imagine you're a clinical psychologist. You're investigating something called Smith's cognitive therapy. I just made that up. It is a cognitive therapy similar to Beck's cognitive therapy. You believe it should be effective in improving levels of psychological health in depressed clients. For what it's worth, there's different kinds of therapies that are effective with depression, and the cognitive therapies are among those that are prescribed for people suffering from depression. You're going to conduct an investigation in which you investigate the effectiveness of a specific kind of therapy, and specifically the length that this therapy is, the length of therapy sessions, the number of therapy sessions that are used in treating somebody using this Smith's cognitive therapy. Here's your initial research question that you're going to investigate in this study. Is the length of therapy related to psychological health? Is it true that the more therapy sessions somebody gets, the better their psychological health becomes? Is it true that 5 sessions is better than no sessions? Is it true that 10 sessions is better than 5? That's going to be one of the research questions you investigate in the study. In your investigation, your dependent variable is going to be scores on a measure of psychological health. Let's assume that you measure psychological health with some kind of instrument that gives you scores that are on an interval scale. Scores could potentially range from 0 to 60, and higher values indicate better psychological health. To keep things simple, you conduct an investigation with 18 subjects. In real-world research, you'd want a lot more than 18 subjects to have adequate statistical power. By keeping it down to 18 will make it easy for me to show figures and numbers in the tables and figures that I'm going to show in this lecture. Eventually, we'll see that we're going to manipulate two independent variables in the investigation. Independent variable A, first independent variable, is length of therapy. This independent variable is going to consist of three treatment conditions. 1/3 of your subjects will be assigned to level A1. They will get 0 weeks of therapy. In other words, they get no therapy at all. They'll be the baseline against which we compare the other two conditions. 1/3 of your subjects will be assigned to level A2. They will get 5 weeks of therapy. And finally, 1/3 of your subjects will be assigned to level A3. They will get 10 weeks of therapy. The levels of this factor appear as columns in the following table. Scores on the dependent variable appear in the column. For now, let's assume that there is no factor B. For now, let's assume that there is no factor B, which I'm going to describe in a few minutes. For now, let's pretend the only factor in the investigation is factor A, length of therapy. Focus only on factor A, the columns. Here's a table that illustrates our factorial design and also provides scores on the dependent variable. Let's shrink the page down so we can get the whole thing in. You'll see me refer to this table many times as I go through this lecture. For the moment, pretend that there is nothing over on this side of the table. For the moment, pretend there is no factor B type of depression. We'll talk about that later. For now, let's pretend the only factor in the investigation is factor A, independent variable A, length of therapy. In your investigation, you assign 6 participants to experience 0 weeks of therapy. They're going to be the control group against which we compare the other groups. What are these numbers in the column? It's their scores on the dependent variable. Remember, this was a variable where scores range from 0 to 60. Higher values indicate better psychological health. At the end of the study, this person had a psychological health score of 29. This one had a psychological health score of 30, and so forth. These are the scores of the dependent variable for the 6 people in your 0-week condition. 1/3 of the participants were assigned to level A2. They got 5 weeks of therapy. These are their scores on the dependent variable at the end of the investigation. And then finally, there were 6 participants assigned to level A3. They got 10 weeks of therapy. This column contains their scores on the dependent variable at the end of the investigation. This is how we manipulated factor A, length of therapy. But as long as you're conducting an investigation, isn't there an additional research question that you can investigate in the same study? Sure. Why don't we also investigate this research question? Does the effect of the length of therapy depend on what type of depression the client suffers from? Yes, it turns out that there's more than one type of depression. We're going to use type of depression as a second factor in the investigation. Type of the depression is going to be factor B. Independent variable B, factor B, is going to be type of depression. Let's imagine you designed your study so that half of the participants are going to constitute level B1. Half of your participants suffer from a kind of depression called dysthymia. Dysthymia is a chronic low-grade depression. People that suffer from dysthymia feel depressed much of the time, but it never gets to be extreme depressed symptoms. Think of it as kind of a low-grade depression, but it is chronic. It goes on for a period of time. I believe the DSM requires they have to display the symptoms for at least 2 years before you can classify them as having dysthymia. Half of your participants will suffer from dysthymia. The other half of your participants will be level B2. These will be people that suffer from major depression. Major depression, as the name would suggest, involves much more extreme symptoms. They are extremely sad, extremely hopeless. Sometimes these folks are so sad and hopeless that they don't want to get out of bed in the morning. Major depression tends to be in response to a bad thing that happens in your life. You have a child that you dearly love and the child passes away and you go into major depression. You had a job that you dearly loved and you lost your job and you go into major depression. So our second independent variable, second factor, is going to be independent variable B, type of depression. Half of our participants will suffer from dysthymia and the other half from major depression. Levels of this factor appear as rows in the following table. Remember that rows are horizontal. This is exactly the same table that I showed you before. Now we are going to pay attention to this part of the table. Factor B, type of depression. I set up the table so that half of the participants are in this row. That amounts to 9 participants. These are the folks in level B1, those that suffer from dysthymia. These are their scores on the dependent variable for the 9 people suffering from dysthymia. The second horizontal row is labeled B2. These are the folks that suffer from major depression. There are 9 participants in this condition. These are their scores on the dependent variable. We now have a second factor. We have factor B, type of depression. More of the terminology, more of the jargon that we use with respect to two-way Anova. Researchers speak in terms of factorial design. To describe a factorial design, we refer to the number of levels in each factor. If somebody said, I analyze my data as a 2x3 Anova, this convention, 2x3 Anova, conveys a lot of information. First of all, there's 2 numbers. 2 is a number and 3 is a number. The fact that there's 2 numbers tells you that there were 2 factors in the study. The values of the factors themselves tell you how many levels you had in each factor. One of the factors must have had 2 levels. You know that because you see the number 2 here. And one of the factors must have had 3 levels. You know that because you see the number 3 here. If somebody says, I analyzed it as a 2x3 Anova, that means they have a research design like our research design. Got 3 columns here representing the 3 conditions of factor A. I have 2 rows here representing the 2 rows of factor B. My 3 columns here are the 3 conditions of length of therapy, 0 weeks, 5 weeks, 10 weeks. My 2 horizontal columns here are the 2 conditions of factor B, type of depression. These are the dysthymia people. These are the major depression people. That's what it means if they said, I analyzed it as a 2x3 Anova. What if they say I analyzed it as a 2x4 Anova? Once again, you know you've got 2 factors. You've got 2 factors because there's 2 numbers. This is a number, this is a number, so you must have had 2 factors. The values of the numbers themselves tell you how many levels you had. One of the factors must have had 2 levels, the other factor must have had 4 levels. For example, we could have modified the current study so that factor A had 4 conditions rather than 3. Maybe this column represents people that got 0 weeks of therapy. These are the people that got 5 weeks therapy. These are the people that got 10 weeks therapy. These are people that got 15 weeks of therapy. The 2 horizontal rows still represent 2 kinds of depression. This row represents people with dysthymia. This row represents people with major depressive disorder. Could have expanded it to be a 3x4 Anova. You still have 2 factors because you have 2 numbers. This is a number, this is a number, so there are 2 factors. But now I've got 3 levels of one of the factors. So first of all, factor A, I've got 4 levels of it. 0 weeks of therapy, 5 weeks of therapy, 10 weeks of therapy, 15 weeks of therapy. That's what 4 represents. What could the 3 represent? I must have 3 different kinds of depression. Maybe this row represents people with dysthymia. Maybe this row represents people with major depressive disorder. Maybe this row represents people with bipolar disorder. I'm analyzing it as a 3x4 Anova. That's what we mean when we talk about the 2x3 factorial design convention. Now, I was on page 140-12. Sometimes in review sessions, students would ask me to go into this whole business in more detail. Therefore, I cooked up some additional pages of lecture, and it is available in Canvas in the current module as a supplementary download. When you read the directions for the current module, it'll tell you where to look in the Canvas module to find it. And when you download that PDF with the additional pages, you will see 5 additional pages of lecture notes. I'm not going to spend time in this video going over these lecture notes because most students didn't seem to need it, but for those of you that want a little bit more detailed explanation on this business of the 2x3 Anova convention, there's a supplementary download, supplementary PDF in the current module. You can download it and it will have these 5 pages. This is one of the pages, this is the second page, this is the third page, this is the fourth page, and there's the 5th page. So for those of you that want a little bit more instruction on this business of the 2x3 factorial design, you'll find it in that supplementary PDF download that you can get in the Canvas module for the current module. Now, for the rest of us, let's go back to our Psych 299 course pack. In the Psych 299 course pack, we resume lecturing here. Page 140-13. 140-13, we're still talking about the terminology of analysis variance. We come to the concept of a cell. Definition for a cell. There's more than one way to define it. We can define cell this way. A cell represents the combination of one level of one factor with one level of the other factor. I think of a cell as being a location in a table. A cell is a location where the column for factor A, where a specific column for factor A intersects with a specific row for factor B. Refer to the table on the next page. With a between subjects design, a given subject is going to fall in just one cell. On page 140-14, this is a table that illustrates our research design, same research design we talked about before. This location is a cell. This is cell A1B1. It represents the intersection of level A1 under factor A with level B1 under factor B. Level A1 was the people that got 0 weeks of therapy. Level B1 under factor B was people that had dysthymia. So there would be, what was it, 3 people here? 3 people that suffered from dysthymia and got 0 weeks of therapy. Cell A2B1, we're still looking at people that suffer from dysthymia, but these are the 3 people that got 5 weeks of therapy and so forth. So spot in this table is a cell. It's a spot in the table where a specific level of factor A intersects with a specific level of factor B. We move on to page 140-15. Come to an important concept. In fact, let's enlarge the page a little bit and let's take things one step at a time. This is going to be the main emphasis of the rest of this lecture, and this is going to be the focus of your online Canvas quiz that you'll take sometime over the next week or so to demonstrate that you understand the kinds of effects that are possible in Anova. There are two different types of effects that are possible with two-way Anova. And by that, I don't mean there's 2 effects that are possible, but 2 different types of effects, 2 two qualitatively different kinds of effects that are possible with two-way ANOVA. One kind of effect that's possible we call a main effect. Main effect is the effect on the dependent variable of changing the levels of a given factor while ignoring all the other factors in the study. Main effect is similar to the concept of a treatment effect in one-way ANOVA. Main effect in two-way ANOVA is very similar to the concept of a treatment effect in one-way ANOVA. In one-way ANOVA, if one of your conditions was significantly different from one of the other conditions, you had a treatment effect. The same thing applies in one-way ANOVA. If you get a main effect for a given factor in two-way ANOVA, it means that when you're looking at that factor, at least one of the treatment condition means was significantly different from at least one of the other treatment condition means. So main effect is really nothing new. Main effect in two-way ANOVA is the same thing as a treatment effect in one-way ANOVA. Most students in this class don't have much trouble with the concept of main effect. If they struggle at all, here is where they struggle. It's with the second kind of effect that's possible in two-way ANOVA. The second kind of effect that's possible in two-way ANOVA we call an interaction effect. Interaction effect means that the effect of changing the levels of one factor differs for different levels of the other factor. I will say that again. In two-way ANOVA, an interaction effect means that the effect of changing the levels of one factor differs for different levels of the other factor. That should not make any sense to you right now. That's a fairly obtuse definition, but I'm going to give you an alternative definition, alternative way of thinking about it, and I'm going to show you a bunch of graphed results that illustrate what I mean by interaction effect. I have a note here. Very often the researcher is most interested in the interaction effect. Very often the whole reason they analyze their data using two-way ANOVA is because they wanted to see whether they had a statistically significant interaction effect. It is a big deal. Okay, concept of interaction effect is a complex topic. I'm going to cover it in more detail in a few minutes. First, let's go in more detail over this more elementary concept, the concept of a main effect. Most of you will find the concept of main effect easier to understand, so we'll tackle that first. Main effects. The F-test for a main effect involves a comparison among the level means of a given factor. Remember I said earlier, a main effect in two-way ANOVA is essentially the same thing as a treatment effect in one-way ANOVA. Complicating matters is the fact that there's actually two possible main effects that are possible in a two-way ANOVA. Remember, we have two factors in a two-way ANOVA, two independent variables in a two-way ANOVA. That means there's two main effects that are possible. In a two-way ANOVA, there'll be one F-test to assess the main effect for factor A, length of therapy in our current fictitious investigation. So we'll compute one F statistic to see whether we have a significant main effect for factor A. There will be a separate F-test to assess the main effect for factor B, type of depression. Is there a significant difference in psychological health between people that have dysthymia versus major depressive disorder? We will compute a separate F-test to see whether that main effect is statistically significant. Still talking about the concept of a main effect. To assess the main effect for a given factor, you collapse across levels of the other factor. In other words, you pretend that the other factor does not exist. This is an issue that is on your study guide. Your study guide asks something like, what does it mean when we say we collapse across levels of a given factor? This is where in the course pack we talk about this issue. To assess the main effect for a given factor, you collapse across levels of the other factor. In other words, you pretend that the other factor does not exist. See figure 140.4 for our research design. To assess the main effect for factor A, you collapse across levels of factor B. To assess the main effect for factor B, you collapse across levels of factor A. Let's take these one at a time. First of all, to refresh your memory, this is the table that illustrates our research design. Remember, the current 2A Anova, we have two factors. Factor A is length of therapy. We're comparing people to get 0 weeks of therapy versus 5 weeks of therapy versus 10 weeks of therapy. In our investigation, factor B is type of depression. We're comparing people that suffer from dysthymia to people that suffer from major depression. First up, let's imagine we want to look at the main effect for factor A. I want to know whether length of therapy has an effect on scores on my dependent variable, psychological health. Main effect for factor A. Is there a statistically significant difference between at least two of the conditions that I have under factor A? In order to determine that, I'm going to collapse across levels of factor B. I'm going to pretend that factor B does not exist. I redraw my table to illustrate that concept. Let's make this a little bit smaller still, just to make this real easy to see. I'm looking at page 140-18. To assess the main effect for factor A, you collapse across levels of factor B. Notice I have erased the line that had separated the dysthymia people from the major depressive people. For all practical purposes, there is no factor B now. For all practical purposes, it does not exist. All that I have is factor A. I'm going to look at the 6 people that got 0 weeks of therapy. I'm going to determine what's their mean score on the dependent variable, psychological health. I'm going to look at the 6 people that got 5 weeks of therapy. What's their mean score on psychological health? I'm going to look at the 6 people that got 10 weeks of psychotherapy. What's their mean score on psychological health? And I'm going to compare these 3 means. Is there a significant difference between at least 2 of the 3 means that I have here? If yes, I've got a significant main effect for factor A. Notice I've collapsed across levels of factor B. I've ignored factor B. I've pretended that there is no factor B. That's what we mean when we say we collapse across levels of a given factor. Okay, at this point, the only thing I've looked at is the main effect for factor A. Isn't it also possible that there's a main effect for factor B? Well, if I want to investigate the main effect for factor B, remember factor B is type of depression. If I want to investigate the main effect for factor B, then I'm going to want to collapse across levels of factor A. I illustrate what that would look like on the next page, on page 140-19. To assess the main effect for factor B, I collapse across levels of factor A. Notice I have erased the lines that separated the 3 conditions of factor A. For all practical purposes, there is no factor A anymore. The only thing that exists is factor B. I've got the 9 people in condition B1. These were the 9 people that suffered from dysthymia. I'm going to determine what's their mean score on psychological health. That's represented by this symbol. I've got the 9 people that suffered from major depressive disorder. What's their mean score on psychological health? It's represented by this symbol. Is there a statistically significant difference between this mean versus this mean? If yes, that indicates I've got a statistically significant main effect for factor B. I have collapsed across levels of factor A. I pretended there was no factor A. That's what we mean by collapsing across levels of the other factor. If I'm going to do significance testing, then I'm going to want to state a null hypothesis. You'll remember me saying earlier in the semester that significance testing is all about stating a statistical null hypothesis and testing it. Statistical null hypothesis is almost always a prediction that in the population there's no difference between your various treatment conditions that are being compared. Almost always the researcher hopes that he or she will be able to reject the null hypothesis. Well, how do we state the null hypothesis for a main effect if we're doing factorial Anova? Let's blow this type up a little bit more so it's easier to see. Null and alternative hypothesis for main effects in factorial Anova. Null hypothesis and alternative hypothesis for a main effect is going to be pretty much the same as the null and alternative hypothesis for a treatment effect in one-way Anova, except we're going to have to use letter subscripts to acknowledge the fact that we've got two different factors here. There's a factor A and a factor B. Now, factor A had three treatment conditions, so this is the way we would state the statistical null hypothesis for the main effect for factor A. Null hypothesis would say, in the population, the mean score for level A1 is equal to the mean score for level A2 is equal to the mean score for level A3. Null hypothesis says in the population there's no difference between these three treatment conditions with respect to their mean scores on the dependent variable. You're the researcher, you probably hope you'll be able to reject this null hypothesis. By the time you're done, you hope you'll be able to show that at least one of these treatment conditions is significantly different from the other. If yes, then you'll get some support for your alternative hypothesis. How do you state the statistical alternative hypothesis for the main effect for factor A? You say, not all mu A's are equal. Not all mu A's are equal. That is your alternative hypothesis in testing the main effect for factor A. But that's only one of your factors. What about factor B? You've got to state a null and alternative hypothesis for it, and we'll do it in a similar way, except we'll use B subscripts instead of A subscripts. And remember, you only had two conditions of factor B in this case, so we'll take that into account. This is the way that we state the null and alternative for factor B. For factor B, null hypothesis for the main effect for factor B. In the population, the mean score for condition B1 is equal to the mean score for condition B2. You state in the population there's no difference between these two treatment condition means. You hope to be able to reject that. If you can reject it, you get support for the alternative hypothesis, which says not all mu B's are equal. This is the same way that we would state statistical null and alternative hypothesis for independent samples t-test or for a one-way analysis variance if we had only two treatment conditions. Notice the way that we stated these was pretty much the same way that we would state them if we're doing one-way Anova, except, let's make this a little bit smaller, except we've got to use these letter subscripts to make it clear which factor we're talking about. I used the A as the letter subscript when talking about factor A. I used B as the letter subscript when talking about factor B. Now that is main effect. Unfortunately, in my notes here, I immediately go to a new topic, but in reality, psychologically, we need to kind of pause and catch our breath because we're leaving behind the subject of main effects and we're going to a totally different subject, the subject of interaction effects, which is new territory, new terrain. So let's pause and gather our thoughts before we move forward. Let's also get a drink of water so our mouth doesn't get too dry during this long lecture. We now move to the topic of two-way interaction. I defined it earlier. Let's look at an alternative definition for two-way interaction. I gave you one definition for two-way interaction earlier, which is a totally acceptable way to define it. A lot of students find it easier to understand if we instead define two-way interaction this way. A two-way interaction means that the relationship between one factor and the dependent variable is different at different levels of the second factor. I'll say that again. Two-way interaction means that the relationship between one factor and the dependent variable is different at different levels of the second factor. In the current investigation, with the variables we're studying in the current investigation, two-way interaction means that the relationship between length of therapy and psychological health is different for different types of depression. Now that's kind of difficult to understand if you get it only in verbal terms. We will see pictures that illustrate the concept of interaction. Here's two words that I always want you to have in the back of your mind whenever you're thinking of interaction. Interaction essentially means it depends. Is there a relationship between factor A and the dependent variable? Well, it depends. It depends on which condition under factor B you're looking at. I will illustrate that with some pictures. And let's back off a little so we can see this picture. I'm on page, let's back off a little bit more than that. I'm on page 140-21. Here's a figure that illustrates the relationship between length of therapy and psychological health. This is the kind of figure that I'll use pretty much throughout the remainder of this lecture to illustrate interaction effects and also to illustrate main effects. This is a fairly standard convention for illustrating the results from a two-way Anova. With this approach, take one of your factors, in this case factor A, length of therapy, list it on the horizontal axis. Length of therapy is the x-axis down here, and the conditions of factor A I represent as points on the x-axis. This point represents people that got 0 weeks of therapy. This point is those that got 5 weeks of therapy. This point is those that got 10 weeks of therapy. The x-axis, the vertical axis, is my dependent variable, scores on the dependent variable, psychological health. In this case, scores could range from low values to higher values, and higher values represent better psychological health. But wait a minute, there was a second factor in my investigation. Factor B was type of depression. How am I going to represent factor B in my study? Well, within the body of the figure, I'll use different lines to represent the different conditions of factor B. I'll represent a solid line to represent scores for people that suffer from major depression. Solid line, here's the little legend up here at the top that tells us that solid line represents those with major depression. Here's the scores, the average scores of the dependent variable that we got for the people that suffered from major depression. I'll use a different line, a dashed line, to represent results for people that suffer from dysthymia. So this dashed line represents results for the people who suffer from dysthymia. Now, this figure illustrates statistically significant interaction effect. It illustrates a statistically significant interaction between length of therapy and type of depression in determining scores on psychological health. Earlier, I said interaction effect is all about the words "it depends." Notice how that's relevant here. Imagine I got these results and I've plotted them in a figure. I'm walking down the hall and a faculty colleague knows I've been analyzing my data, and colleague asks me, "Larry, what did you get with this study that you conducted? Is it true that length of therapy has an effect on psychological health? Is it true that the longer people are in therapy, the better their psychological health becomes?" My answer in this case would be, it depends. It depends on what kind of depression the individual is suffering from. For example, if I focus on the solid line, this is the people that suffer from major depression. Remember my legend up here. If I look at the results just for the people that suffered from major depression, the answer is yes. There is a relationship between length of therapy and psychological health. When I look at the people that suffer from major depression, if they don't get any weeks of therapy, their psychological health is low. If they get 5 weeks of therapy, psychological health is better. 10 weeks of therapy, psychological health is better still. So yeah, length of therapy has an effect on psychological health when I focus on people that suffer from major depression. However, I get a different set of results if I focus instead on the people that suffer from dysthymia. In this case, length of therapy doesn't have any effect on psychological health if I look only at those people that suffer from dysthymia. Notice, people with dysthymia that got 0 weeks of therapy show mediocre psychological health. 5 weeks of therapy still show mediocre psychological health. 10 weeks of therapy, they still show mediocre psychological health. So, does length of therapy have an effect on psychological health? It depends. It depends on which condition they're in under the other factor, under the type of depression factor. This is what an interaction is all about. The relationship between one factor and the dependent variable is different at different levels of the other factor. Relationship between factor A and the dependent variable is different at different levels of factor B. I will show additional examples of interactions as we go through this. Let's get a little bit closer on the lecture notes to fill in some blanks here. I'm on page 140-22. Some of this I've already said. 140-22. Graphing results from two-way Anova. What's a standard kind of convention for graphing results from two-way Anova? Standard convention is to use points on the x-axis to represent the levels of factor A, and to use different lines within the figure to represent the different levels of factor B. In most cases, factor B should be the independent variable that has the smallest number of levels so that you'll have the fewest lines. And yes, that is what we did with the previous figure. Let's go back and make sure what I just said makes sense. Graphing results from two-way Anova. I use points on the x-axis to represent the different levels of factor A. Factor A was length of therapy. This is a point, this is a point, this is a point on the x-axis. Use points on the x-axis to represent levels of factor A. To represent levels of factor B, I use different lines within the body of the figure. I use the solid line to represent the major depression level of factor B, and I used a dashed line to represent the dysthymia level of factor B. That is what was said in this bit. Graphing the results of Anova using points on the x-axis to represent levels of factor A, etc. Now, let's dig deeper on this idea of interaction effect. I promised I was going to show more than one example of an interaction effect. Researchers speak in terms of two different kinds of interaction that are possible. They talk about the difference between a disordinal interaction versus an ordinal interaction, and it's not a complex concept. If it's a disordinal interaction, that means that the lines cross within the body of your figure. And yes, I'm going to show you an example of what that looks like. With an ordinal interaction, the lines do not cross within the body of your figure, but the lines are non-parallel. What do you mean by that? Well, let's see some examples. And let's make this smaller again. Page 140-23 illustrates disordinal interaction. Disordinal interaction is kind of interaction that I've talked about so far. With a disordinal interaction, the lines cross within the body of your figure. Yes, you can see that the line for the people with major depression crosses the line for the people with dysthymia. That makes this a disordinal interaction. Now, some students come out of an elementary stats class and think that for you to say you've got an interaction, the lines have to cross within your figure. But that is not exactly true, strictly speaking. Lines don't actually have to cross to have an interaction, because there's a second kind of interaction. There is an ordinal interaction. With an ordinal interaction, the lines don't cross, but they're non-parallel. This is an ordinal interaction, and it is an interaction effect. Somebody asks me, is it true that the longer people are in therapy, the better they get? Is it true that there's a relationship between length of therapy and psychological health? If I got results like this, my answer would be yes. There is a relationship between length of therapy and psychological health, but the strength of the effect depends on what kind of depression the individual is suffering from. If you look at those people that suffer from dysthymia, there's only a weak relationship between length of therapy and psychological health. Longer they're in therapy, the better they get, but it's not a very strong effect. On the other hand, if you look at people that suffer from major depression, there is a stronger relationship between length of therapy and psychological health. Here, the longer they're in therapy, the much more dramatic the improvements in psychological health becomes. This is an interaction. What we're going to see is the defining characteristic of an interaction effect is non-parallel lines. It's not necessary that the lines cross. The lines just have to be non-parallel to one another. This line is not parallel to this line, and that means I've got an interaction effect. Which brings us closer to the subject of your Canvas quiz. By looking at a figure, you can get a sense as to whether the interaction is probably significant, whether the main effects are probably significant. Now, don't misunderstand me. You still have to analyze your data. You still have to perform analysis of variance. You have to compute an F statistic and get the p-value for your F statistic to see whether the interaction effect is statistically significant, to see whether the main effect for factor A, etc. is significant. You still have to do the statistical analysis to know whether it's actually statistically significant. But I want my students to be able to eyeball the results of two-way Anova and estimate whether you probably have a statistically significant effect or not. That's going to be the subject of small discussion exercise and eventually subject of an online quiz. This will be the subject of an exercise. I give you some guidelines for eyeballing results from Anova and deciding whether you probably have a significant effect or not. First of all, how do I know that I've got a significant interaction? If the interaction is significant, then corresponding segments of lines will not be parallel to one another. Ask yourself this question. Does factor A seem to have one type of effect for one group under factor B, but a different type of effect for other groups under factor B? If yes, you've probably got a significant interaction effect. Does factor A seem to have one kind of effect for one group under factor B, but a different type of effect for other groups under factor B? If yes, you've probably got an interaction. See figure 140.10. Here's where some of my examples come in. Let's get that off screen so we're not confused. Page 140-26, top figure on this page illustrates statistically significant interaction. Here I have a statistically significant interaction between factor A and factor B. How do I know it's statistically significant? Well, look at the corresponding line segments. Now, what do you mean corresponding line segments? Corresponding line segments are line segments that are over and under each other. This line segment is above this line segment, and that makes these two corresponding line segments. This line segment is not parallel to this line segment, and that means I've got a significant interaction effect. Notice how it kind of makes sense. Does factor A have an effect on the dependent variable? Well, it depends. Look at the dashed line. Factor A doesn't seem to have any effect on the dependent variable at all if you looked at the dashed line, level B1, I guess is how I labeled it. However, it does have kind of a complex effect if you look at people in level B2. The solid line is level B2. You get no effect as you move from A1 to B1, but you get a big effect as you move from A2 to, or rather you get no effect as you move from A1 to A2, but you get a big effect as you move from A2 to A3. So yeah, factor A has an effect on scores if you look at the solid line, but not if you look at the dashed line. That means I've got a significant interaction. This line is not parallel to this line, so yeah, I've got an interaction. The bottom figure illustrates non-significant interaction. Notice these two line segments are parallel to one another. These two line segments are parallel to one another. If corresponding line segments are parallel to one another, it's a non-significant interaction. They curve, that is true, but as long as they stay parallel to one another, you don't have an interaction. In fact, I put that into words on the next page, 140-27. If the lines look like railroad tracks parallel to one another, then the interaction is non-significant. So, that is the signature of a significant interaction effect. Non-parallel line segments. Pause. Let that burn into long-term memory. We move to the next kind of effect that I want you to be able to identify, and that is significant main effect for factor A. How do you know you have a significant main effect for factor A? If the main effect for factor A is significant, then at least one set of line segments will be slanted. At least one set of line segments will be sloping, will not be flat. Illustrate that in the next figure or so. Here we go. Let's back off a little bit. I'm on page 140-28. I have a significant main effect for factor A. Here's a figure you have not seen before. Factor A is still length of therapy, 0 weeks, 5 weeks, 10 weeks. Here I've got a significant main effect for factor A. How do I know? Because the line segments are sloping. Notice it kind of makes sense. 0 weeks of therapy, poor psychological health. 5 weeks of therapy, better psychological health. 10 weeks of therapy, better still psychological health. I've got a main effect for factor A. The line segments are sloping. Here's another example of a significant main effect for factor A. These line segments are sloping. That tells me I've got a significant main effect for factor A. Well, wait a minute. These line segments are not sloping. It doesn't matter. As long as you have one set of line segments that's sloping, you've got a main effect for factor A. In this case, it looks like people that get 10 weeks of psychotherapy do better than those that get 5 weeks and 0 weeks of psychotherapy. So yeah, length of therapy makes a difference. Here's another significant main effect for factor A. And now these results would not make much sense, but if we could believe them, people with 0 weeks of psychotherapy do better than those with 5 weeks. People with 10 weeks of psychotherapy do better than those with 5 weeks. These results may not make much sense, but it is a main effect for factor A. You've got line segments sloping, line segments that are sloping. So now you know what a main effect for factor A looks like when you've plotted it in the kind of figure that we've been looking at. Now let's pause. Let's let that burn into long-term memory before we go any further. We come to the third and final kind of effect you can get with 2A Anova, and that is main effect for factor B. You know the main effect for factor B is significant if at least one pair of lines are separated from one another. Main effect for factor B is significant at least one pair of lines are separated from one another. Some examples. Page 140-31. We have a picture of significant main effect for factor B. This is the same study that we've been talking about all along. Dashed line represents people with dysthymia, solid line people with major depression. I have a main effect for factor B. It looks to me like the people that suffer from dysthymia are scoring higher on psychological health compared to the people that suffer from major depression. This result would kind of make sense. It makes sense that people with chronic low-grade depression would be in better psychological health compared to people that are suffering from major depression. This line is separated from this line, so I have a main effect for factor B. What if I had three conditions of factor B? Now here I've kind of squashed the thing because I didn't have much room, but imagine there's a big gap between this line and this line and this line. This line represents people with dysthymia. They are scoring significantly higher in psychological health than this dashed line, which is people that suffer from major depression. They're scoring significantly higher than this dotted line, people that suffer from bipolar depression. If these lines are separated, I have a significant main effect for factor B because my lines are separated from one another. If you have three conditions, it's not necessary that all three lines have to be separated from one another. What if the people with dysthymia scored significantly higher than the other two groups? This line represents people with dysthymia. This is people that suffer from major depression. This is people that suffer from bipolar disorder. There's no difference between the people that suffer from major depression and bipolar disorder, but the people with dysthymia score substantially higher. I have a significant main effect for factor B because this line is separated from these two. Wait a minute, these two lines aren't separated from one another. That doesn't matter. As long as one of the lines is separated from at least one other line, you have a significant main effect for factor B. Well, how am I supposed to know whether the two lines are separated from one another? You have to separate them some so we can see that you've got two different lines here. Anytime there's any confusion or potential confusion, I'll add a note to the figure saying, assume these two lines are close together. You'll see an example of that soon. Pause. You now know the signature for a main effect for factor B. If at least one of the lines is separated from at least one of the other lines, you've got a significant main effect for factor B. Now, you've learned a lot. You've learned how to recognize significant interaction effect, significant main effect for factor A, significant main effect for factor B. Now comes the bad news. It gets more complicated than that. In a given investigation, you can get multiple significant effects. If you do two-way Anova, it's possible to get any combination of significant effects. Significant interaction effect, significant main effect for factor A, significant main effect for factor B. Maybe your interaction effect is significant, main effect for A is significant, but not the main effect for B. Maybe there's a main effect for factor A, main effect for factor B, but not an interaction. Any number of combinations of significant effects are possible. I want you to be able to recognize that when you're looking at results from a two-way Anova that are graphed. Further complicating matters is the fact that not all effects are created equal. Some types of effects are more important than other kinds of effects. Here's the basic rule. Let's blow this up so this is easier to read. Basic guidelines. If the interaction effect is significant, then the primary interpretation of the analysis of variance should rest on the interpretation of this interaction effect. If the interaction effect is significant, then do not interpret main effects for factor A and factor B, even if they are significant. Now, there's going to be exceptions to this rule. Some of you are going to go into graduate school. You will take a more advanced class on statistics, and you'll learn that there are certain situations that you don't observe this rule. But this is the rule that's typically taught in elementary statistics class, and this is the rule I want my students to go by. The basic rule, if your interaction effect is significant, then primary interpretation of the results depends on this interaction effect. Don't interpret main effects for factor A and factor B, even if they're significant. If the interaction effect is non-significant, then you can interpret main effects for factor A and factor B if they're significant. Implication for looking at pictures that illustrate results from Anova. First, look for evidence of an interaction, that is, corresponding line segments that are not parallel. If you've got corresponding line segments that are not parallel, you've got an interaction. That's what you'll interpret. You should interpret main effects only if there's no interaction effect. I am going to show you examples of what this looks like. On your Canvas quiz, what I call a skill quiz here, on your Canvas quiz, you'll be shown a figure. You'll be asked, is there a significant A by B interaction? How do you know? A by B interaction, that's the kind of symbols that we use to represent a two-way interaction, the two-way interaction that I've been talking about throughout this lecture. Is there a significant A by B interaction? How do you know? I want you to fill in a response where you tell me whether there's a significant interaction and what is it about this figure that tells you whether there's an interaction or not. Question number 2, is there a significant main effect for factor A? How do you know? Fill in the blank below. It continues. Is there a significant main effect for factor B? How do you know? You'll fill in the blank telling me whether there's a main effect for factor B and how you know whether there's a main effect for factor B. My guideline. If the answer to question 1 is yes, that is, if there's a significant interaction, then your answers to questions 2 and 3 must be not relevant. In other words, the significant interaction trumps all other significant effects. If the answer to question 1 is yes, then the answers to questions 2 and 3 must be not relevant. In other words, significant interaction trumps all other significant effects. To go back and look at these questions that I just went over. Question 1, is there a significant A by B interaction? If you answer, yeah, there is a significant A by B interaction, I know because the lines are not parallel to one another. If you're saying, yes, there's a significant interaction, your answers down here should be not relevant. When I ask about main effect for factor A, you'll say not relevant. When I ask, is there a main effect for factor B, you say not relevant. Question 1, is there significant interaction? If you say yes there, then you should say not relevant for questions 2 and 3. Yes, I will give you examples of that. Here is your cheat sheet where I kind of put all these ideas together. In summary, when you're looking at a figure where I've graphed results, you know that there is a significant interaction if corresponding line segments are not parallel. You know that there is a main effect for factor A if corresponding line segments are parallel but they're slanted. You know there's a significant main effect for factor A if the lines are parallel but they're slanted, they're sloped. Finally, you know there's a significant main effect for factor B if the lines are parallel but they're separated from one another. There's nothing new here. It's the same information I gave you earlier, but I put it all together in one cheat sheet that you'll have in front of you as you go through the exercise. Speaking of which, let's skip past this. This talks about Canvas quiz that you're eventually going to do, and what pages to look at, and these are the pages to look at. Ultimately, you're going to do a Canvas quiz, which will be 5 multiple choice questions. You go to Canvas, you go into this module. When you're ready, you'll click and start the Canvas quiz for the current module. And that Canvas quiz will consist of 5 multiple choice questions, which will be based on this exercise. Now, this exercise does not immediately follow the pages in the course pack you're looking at. If you're looking at the paper course pack that you bought at the SVSU bookstore at the beginning of the semester, you need to skip toward the back of the course pack. Go to Appendix E. Appendix E is the exercise appendix. Skip through the pages of Appendix E until you get to page E22. This exercise is going to be on pages E22 through E24. do pull this exercise out and look at it, because I'm going to go over this exercise at this time. This is what your 4-point Canvas quiz will be based on. Pause the video if you need to pull out that exercise. This is one exercise that you won't download from Canvas. You already have it in your course pack. Okay, in your course pack, in the E pages, beginning on page E22, we have, this would be a small group discussion exercise. Given the current state of affairs, you won't be doing it in small groups, so we're going to be doing it here and now. It is called Interactions and Main Effects, exercise 140.E2. Let's see if we can go in a little tighter on this. No, I guess we can't go in a little tighter on that. We'll have to leave it here. Okay, the exercise instructions, the study. Assume you've conducted a study in which subjects have ingested some quantity of caffeine and then solved a set of puzzles. You then measured their performance in solving these puzzles. The study has two independent variables. Independent variable A was amount of caffeine. Independent variable A, amount of caffeine, consisted of 3 levels. There's a 0 milligram of caffeine condition, 200 milligram of caffeine condition, and a 400 milligram of caffeine condition. For what it's worth, this is like drinking no coffee. This is like drinking 1 big cup of coffee. This is like drinking 2 big cups of coffee. So factor A is amount of caffeine. You have a second independent variable in your study. Independent variable B is difficulty of the puzzles. Independent variable B consists of 2 levels. Half of your people solved easy puzzles, the other half of your people solved difficult puzzles. Dependent variable in the study is performance in solving puzzles. Let's imagine this is operationally defined as the number of puzzles that the subject solves in a 30-minute period. You've conducted this investigation. You have results from the investigation. You're now going to graph the results and interpret what the results appear to mean just by looking at the graph. Brings us to your task. On the following pages are a number of figures that graph some possible outcomes from this study. Your job is to determine which effects are probably significant in a given study based on the figure for that study. Specifically, you'll answer each of the 3 questions. Let me read that again. Specifically, you'll answer each of the 3 questions under each of the figures. You'll write your answers directly in the small space below each figure. In doing this, follow the recommendations that I gave in class. Remember that amount of caffeine is factor A. Remember, difficulty of puzzles is factor B. And respond to all 4 of the outcomes in the following pages. This is the real one for your online quiz. In previous semesters, I actually gave my students a practice quiz along these lines. I found that it was a bad idea because some students would get confused and they'd have the practice quiz in front of them when they were doing the 4-point Canvas quiz. So I wound up getting rid of that so that people would not get hurt on the quiz because they were looking at the wrong figures. I'm going to do this kind of slow-like. I'm going to show you just the figure and give you a chance to think about the results before I reveal the results. Normally in a lecture like this, I would not reveal the answers to the quiz, but because we're on kind of a short time frame now under our current circumstances, and because you folks don't have much of an opportunity to interact with one another and share answers with one another, I'm going to show you a figure, give you a chance to stop this video, fill in the answers on your exercise sheet, which should be in front of you right now, and then unpause the video and see what the correct answers are. Needless to say, you don't necessarily have to pause the video. You can just let it play and see what the answers are, but I would encourage you to do this because it'll be good practice for you to get you ready for the kinds of questions that you're likely to have to answer on the test that's coming up, a test where you won't have a video to look at. Except I guess if it's open book, open note, maybe you would have a video to look at. I'll think about that after I'm done making this video. Let's see, outcome number one. Here's our investigation. Factor A is amount of caffeine consumed. These are the people who got 0 milligrams caffeine. These got 200 milligrams caffeine. These got 400 milligrams caffeine. Factor B, let's bring that back. Factor B was difficulty of the puzzles. The dashed line gives us results from people with easy puzzles. Solid line, results from people with difficult puzzles. Dependent variable plotted here is their performance. Let's assume higher scores mean more puzzles solved. If you got results like this, 3 questions to answer. Question number 1. Is there a significant interaction between factor A and factor B? Is there a significant interaction between amount of caffeine consumed and difficulty of puzzles? Yes, no, how do you know? What is it about the figure that tells you whether you've got an interaction or not? Question 2, do you have a significant main effect for factor A, amount of caffeine? How do you know? In fact, in question 3, is there a significant main effect for factor B, difficulty of puzzles? How do you know? Pause the video, try to answer those questions, and then unpause the video and you'll see what the correct answers are. Okay, you've jotted down your answers. Dr. Hatcher will reveal his answers now. Question 1, is there a significant A by B interaction? How do you know? Correct answer, no, there's no interaction. How do you know? The lines are parallel. This line is parallel to this line. Amount of caffeine has exactly the same effect when I look at the difficult puzzle people as when I look at the easy puzzle people, so there's no interaction. Question number 2, is there a significant main effect for factor A, amount of caffeine? No, there's no main effect for factor A, amount of caffeine. How do I know? Well, the lines are not sloping. This line is flat, this line is flat. When your lines are flat, you don't have a main effect for factor A. Question C, is there a main effect for factor B, difficulty of the puzzles? Yes, there is a main effect for factor B. How do you know? The lines are separated. This line is separated from this line. People with easy puzzles answered a lot more puzzles compared to those with difficult puzzles. That kind of makes sense. So yeah, I've got a significant main effect for factor B. This is outcome number 1. Let's go to outcome number 2. And let's scroll this careful like. Let's imagine down at the bottom of the page, outcome number 2. You got results like this. You've got 3 questions. A, is there a significant interaction? How do you know? B, is there a significant main effect for factor B? How do you know? C, is there a significant main effect for factor B? How do you know? Pause the video, fill in your answers, then you can resume the video and see what the correct answers are. You have filled in the blanks. What does this Dr. Hatcher think is the answer to these questions? A, is there a significant A by B interaction? Yes, there is a significant A by B interaction. How do you know? Lines are not parallel. This line segment is not parallel to this line segment. That's enough to tell me I've got an interaction. Wait a minute, well, these 2 line segments are parallel. That doesn't matter. As long as I've got one corresponding set of line segments that are not parallel, you've got an interaction. Now, question B, is there a significant main effect for factor A? How do you know? This may be the single most challenging question in the quiz. What's the correct answer to question B? Not relevant. Remember my guide that I gave you before. Anytime you look at a figure like this, I ask, is there an interaction? If you say yes, there is an interaction, and I proceed to ask, is there a significant main effect for factor A? You should say not relevant. If there's a significant interaction, the interaction effect trumps all the other effects. You don't interpret main effect for factor A or factor B, even if they're statistically significant. So when I say, is there main effect for factor A? You say not relevant. When I ask, is there a main effect for factor B? Once again, you say not relevant. That is outcome 2. Let's go to another outcome. I'm on page E24. Get results like this. Notice I've added a note here. Assume that these lines are close together. Anytime there's any question, I'll give you a note to clarify things. Let's assume the lines are close together. Pause the video, answer questions A, B, and C. Interpret these results. Once you've filled in your blanks, then you can resume the video, see what the correct answers are, and test your understanding of interpreting results from Factorial Anova. Pause the video. And you've resumed the video. Let's see what Dr. Hatcher's answers are. Question A, is there a significant A by B interaction? How do you know? No, there's no interaction here. How do you know? The lines are parallel to one another. I'm getting the same effect regardless of whether I looked at the dashed line or the dotted line. Question B, is there a significant main effect for factor A, amount of caffeine? How do you know? Yes, there is a main effect for factor A, amount of caffeine. How do you know? My lines are separating. People who got 400 milligrams caffeine did better than those with 200 milligrams caffeine, who in turn did better than those with 0 milligrams caffeine. So yeah, there's a main effect for amount of caffeine. Well, question C, is there a main effect for factor B, difficulty of the puzzles? Nope, there is no main effect for factor B. How do you know? Because the lines are not separated. I added a note. Let's assume the lines are close together. Difficulty of the puzzles made no difference. Finally, we come to our last outcome, outcome 4. These are the kind of results that I often get when I do research. Take a look at the figure, fill in your answers to questions A, B, and C. Pause the video as you do so, and once you've answered the questions, resume the video, and you'll see what my answers are. Outcome 4, question A. Is there a significant A by B interaction? No. How do you know? Because the lines are parallel. The solid line parallel to the dashed line. Question B, is there a significant main effect for factor A, amount of caffeine? No, the lines are not sloping. 0 milligrams of caffeine did like this. 200 milligram group didn't do any better. 400 milligram group did not do any better. I got no main effect for amount of caffeine. Well, what about difficulty of puzzles? Is there a significant main effect for factor B, difficulty of puzzles? No. How do you know? Because the lines are not separated. I notice I added a note there. Assume that these lines are close together. I don't have a main effect for difficulty of puzzles because the lines are not separated. Okay, that is the kind of thing that I want you to be able to do. Once you have studied the notes for this module, once you have studied this exercise and you feel comfortable with it, you'll be able to go to the module for the current module in Canvas, go to the Canvas quiz for this module, start that Canvas quiz. There'll be 5 multiple choice questions. There will be 5 multiple choice versions of the open-ended questions you saw in this exercise. You remember, you must have this completed exercise in front of you before you start the Canvas quiz, because it'll be asking about questions about these figures, and the figures will not appear in Canvas. You've got to have them on paper in front of you. And this also, and this will be the name of the Canvas quiz. It will be called VQ 140 Interactions. VQ 140 Interactions 140-E2. It'll be available starting midnight tonight, and it'll be available for 1 week. What's below there? Nothing below there. And that brings me to the end of this lecture. This has been a long lecture, hasn't it? Okay, you've got the lecture notes that you need. This is the last of the lecture videos that I am uploading. There were modules for the current unit that I had hoped to cover, but we've run out of time. You will be tested only on the lecture modules that are complete, either because they were already complete in your course pack or because they were blanked out and I filled them in by giving you these video lectures. Take a look at your study guide, look at your course pack, study your course pack with study guide in hand. You should have downloaded some lecture notes from Canvas with the previous video lectures that I've given. Study those lecture notes with your study guide in hand. Flag those things that are giving you trouble. We will have an online review session 2 days before the test that gets you ready for the test. You'll be getting an email from me in which I give you the details about that online review session. Online review session is optional, but I want to make it available to those of you that have questions. We will take the test online as scheduled. We will have the online review session for those of you that are interested in it. So keep your eyes open for future emails from me in which I give you details about those upcoming events.